I've lived long enough to remember when the idea of leaving our solar system was pure science fiction. I was in my 20s when Voyager 1 launched in 1977, watching it on a grainy television set, never imagining I'd live to see what happened next. Now, nearly 50 years later, that same spacecraft is still out there, still sending signals back to Earth from a place no human-made object has ever been. And recently, something extraordinary happened that connects Voyager's incredible journey with visitors from beyond our solar system, objects that traveled across the void between stars to pass through our cosmic neighborhood. What's unfolding right now, in my twilight years, is something I never thought I'd witness. The universe is revealing itself in ways that make everything we thought we knew seem small. For those of us who remember the Cold War, the space race, the first moon landing, Voyager 1 represents something more than just a machine. It represents the moment humanity stopped looking inward and started reaching outward. Launched on September 5, 1977, Voyager 1 was part of a twin mission with Voyager 2, designed to take advantage of a rare planetary alignment that happens once every 176 years. The mission plan was simple on paper: fly by Jupiter and Saturn, take pictures, gather data, then drift into space. Simple but profound. I remember the images that came back: Jupiter's great red spot, a storm larger than Earth itself, churning for centuries. Saturn's rings, revealed in detail we'd never seen before, with intricate braids and gaps that told stories of gravity and time. Io's volcanoes, the first active volcanism discovered beyond Earth. Titan's thick atmosphere, hiding mysteries we're still trying to solve today. Those discoveries changed textbooks, they changed how we saw our place in the cosmos. But what Voyager did after completing its primary mission, that's what truly takes my breath away. Most spacecraft, when they finish their work, simply stop functioning. They run out of fuel, their batteries die, they become expensive debris, but Voyager 1 kept going. In 1990, from nearly 4 billion miles away, it turned its camera back toward home and took what Carl Sagan called the pale blue dot photograph. Earth, our entire world, everything we've ever known, reduced to a single pixel of light suspended in a sunbeam. I was 63 years old when I saw that image, and I wept. Everything I'd worried about, everything that seemed important, suddenly felt so small and so precious at the same time. But here's what makes Voyager's story even more remarkable. On August 25, 2012, Voyager 1 crossed the heliopause, the boundary where the sun's influence ends and interstellar space begins. Think about that, a machine built with 1970s technology, carrying computers less powerful than a modern hearing aid, became the first human-made object to leave our solar system. It's now over 15 billion miles from Earth, traveling at roughly 38,000 miles per hour, and it's still communicating with us. Every signal it sends takes over 22 hours to reach Earth, traveling at the speed of light across a distance that would take our fastest rockets 40,000 years to cover. The spacecraft runs on plutonium-238 fuel that slowly decays, generating electricity. When it launched, it had about 470 watts of power. Today, it's down to about 249 watts, barely enough to power a few light bulbs. NASA engineers have been turning off systems one by one to conserve energy, making impossible choices about which instruments to keep alive. They've shut down cameras, platform control systems, even heaters that protect sensitive equipment. Yet Voyager persists, sending back data about cosmic rays, magnetic fields, and the nature of interstellar space itself. Now let me tell you about the visitors that changed everything we thought we knew about our cosmic neighborhood. On October 19, 2017, a telescope in Hawaii detected something that shouldn't have been possible. An object was moving through our solar system on a trajectory that didn't originate from anywhere near the sun. When astronomers calculated its path backward, they realized this object had come from another star system entirely. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar. I was 90 years old when Oumuamua was discovered, and I remember the excitement in the news reports. This wasn't just another asteroid or comet. This was our first confirmed visitor from interstellar space, an object that had traveled for millions or billions of years through the darkness between stars before passing through our solar system. But what made Oumuamua truly strange was its behavior and shape. Initial observations suggested it was cigar-shaped, roughly 400 meters long, but only about 40 meters wide, tumbling end over end every 7.3 hours. No asteroid we'd ever seen looked like this. Then came the real mystery. As Oumuamua moved away from the sun, it accelerated slightly, as if something was pushing it. Comets do this when ice on their surface vaporizes, creating jets of gas that act like tiny rocket engines. But Oumuamua showed no signs of outgassing, no comet tail, no debris cloud. It was accelerating without any visible means of propulsion. Scientists proposed dozens of explanations. Maybe it was covered in frozen hydrogen that vaporized invisibly. Maybe it was incredibly light and porous, allowing radiation pressure from the sun to push it. Maybe it was a fragment of a destroyed planet, tumbling through space for eons. Some even suggested, half seriously, that it might be an alien probe or light sail, though no credible evidence supported this idea. The truth is, we still don't know exactly what Oumuamua was. It passed through our solar system too quickly, and we didn't have time to send a spacecraft to intercept it. By the time we understood what we were looking at, it was already leaving, heading back into the cosmic void. But Oumuamua wasn't alone. On August 30th, 2019, amateur astronomer Gennady Borisov discovered a second interstellar visitor using a telescope he built himself in Crimea. This object, named 2I/Borisov in his honor, was different from Oumuamua in almost every way. Where Oumuamua was dry and mysterious, Borisov behaved exactly like a comet. It had a visible tail of gas and dust, it was actively shedding material, and its composition matched comets from our own solar system. In fact, it contained more carbon monoxide than any comet we'd ever studied, suggesting it formed in an extremely cold environment around another star. What struck me about Borisov was how normal it seemed. After all the mystery of Oumuamua, here was something we could understand, something that fit our models and predictions. It told us that other star systems have comets just like ours, that the process of planet formation creates similar objects across the galaxy. In January 2020, just months before the world changed forever with the pandemic, scientists watched as Borisov broke apart, shedding fragments as it rounded the sun. We got a glimpse into the internal structure of a comet from another star, and it looked remarkably familiar. Now, here's where Voyager's story intersects with these interstellar visitors in a profound way. Both Voyager spacecraft carry what's called the Golden Record, a 12-inch gold-plated copper disc containing sounds and images from Earth. This record includes greetings in 55 languages, music from different cultures and eras, natural sounds like thunder and whale songs, and 116 images showing life on our planet. The record also contains scientific information, including our location in the galaxy using pulsar maps, mathematical and physical constants, and instructions for how to play it. The Golden Record was the brainchild of a committee led by Carl Sagan, designed as a message to any civilization that might someday encounter Voyager in the distant future. When it launched, nobody really expected it would ever be found. Space is unimaginably vast, and the chances of Voyager passing close enough to another star for anyone to notice it are astronomically small. The nearest star to Voyager's current trajectory is Gliese 445, and Voyager won't pass within 1.6 light-years of it for another 40,000 years. But the discovery of Oumuamua and Borisov changed how we think about the Golden Record's purpose. We now know that interstellar objects pass through our solar system regularly. Statistical models based on these two discoveries suggest that at any given time, there might be thousands or even tens of thousands of interstellar objects in our solar system, most too small or too dark to detect. If objects from other star systems are constantly passing through our neighborhood, then the reverse must also be true. Objects from our solar system, including potentially Voyager, might eventually pass through other star systems where they could be discovered. Scientists have identified several interstellar objects that originated from our own solar system, objects like Comet Hyakutake, which passed through our system in 1996 and was then flung outward by Jupiter's gravity, are now traveling through interstellar space just like Voyager. In tens of thousands of years, they might pass through another star system, carrying with them whatever frozen gases and organic compounds exist on their surfaces. But unlike these natural objects, Voyager carries something intentional, evidence of intelligent life, preserved on gold, protected in aluminum, designed to last for billions of years. What really excites scientists today is how Voyager's current mission is helping us understand the environment these interstellar objects travel through. Voyager 1 is measuring the interstellar medium, the thin soup of gas, dust, and cosmic rays that fills the space between stars. This is the same environment that Oumuamua and Borisov traveled through for millions or billions of years before reaching us. Voyager's instruments are detecting particles and radiation that these visitors were exposed to during their long journeys, helping us understand what interstellar space does to objects over cosmic timescales. One of Voyager's most important recent discoveries involves cosmic rays, high-energy particles that zip through space at nearly the speed of light. Inside our solar system, the sun's magnetic field provides some protection against these particles, deflecting many of them away. But in interstellar space, where Voyager now resides, cosmic ray intensity is much higher. Voyager has measured these rays and found they're 3 to 4 times more intense than they are inside the heliopause. This means that any object traveling through interstellar space, like Oumuamua or Borisov, is constantly bombarded by this radiation, which can alter its surface chemistry and break down complex molecules over time. Voyager has also detected something called the bow shock, or rather, it hasn't detected what scientists expected to find. As our solar system moves through the galaxy at about 140 miles per second, scientists predicted there would be a shock wave in front of it, similar to the bow wave a boat makes moving through water. But Voyager's measurements suggest this bow shock might not exist, or might be much farther away than predicted. This changes our understanding of how our solar system interacts with the interstellar medium, and by extension, how other star systems might look from the outside. In November 2023, something particularly exciting happened. Voyager 1 started sending back garbled data, complete nonsense that suggested a serious problem with its flight data system. For months, engineers at NASA's Jet Propulsion Laboratory worked to diagnose the issue, sending commands to the spacecraft and waiting nearly 2 days for each response. Remember, Voyager is so far away that signals take 22.5 hours to reach it and another 22.5 hours to come back. It's like trying to fix a car while only being able to give one instruction per day and waiting until the next day to see if it worked. The team eventually traced the problem to a single corrupted chip in Voyager's memory system. Think about this: a computer chip from 1977, exposed to decades of cosmic radiation, operating in temperatures hundreds of degrees below zero, finally started to fail. But here's the remarkable part: the engineers couldn't simply replace the chip. Voyager is 15 billion miles away. Instead, they had to reprogram the spacecraft to work around the damaged memory, relocating code to different parts of the system and teaching a 47-year-old computer new tricks. In April 2024, they succeeded. Voyager 1 began sending coherent data again, resuming its mission to study interstellar space. This recovery effort demonstrates something profound about human persistence and ingenuity. The engineers working on Voyager today weren't born when the spacecraft launched. They're communicating with a machine older than they are, using technology their grandparents built, solving problems nobody anticipated, across a distance that light takes nearly a day to cross. And they're doing it because the data Voyager sends back is irreplaceable. No other spacecraft has ever been where Voyager is now. No other mission has the opportunity to study interstellar space directly for years or decades. Every day Voyager survives is another day of discovery. The spacecraft's power is declining by about 4 watts per year. At this rate, NASA estimates Voyager 1 will no longer have enough power to operate any scientific instruments by 2025 to 2030. When that day comes, Voyager won't stop moving or cease to exist. It will simply go silent, continuing its journey through the stars without us, carrying the golden record into a future we can barely imagine. But before that silence comes, Voyager is teaching us crucial lessons about long-duration space missions, about how materials age in the radiation and cold of space, about how to operate systems far beyond their design lifetime. These lessons are directly applicable to future interstellar missions. Organizations like the Breakthrough Starshot Initiative are planning to send tiny probes to Alpha Centauri, our nearest star system, using laser-pushed light sails to reach 20% the speed of light. Such a mission could reach Alpha Centauri in about 20 years, compared to Voyager's 75,000-year journey. But to make this work, engineers need to understand what Voyager has taught us about interstellar space, what radiation levels to expect, what temperatures materials will experience, how navigation and communication work across light years. The interstellar visitors we've detected also inform these future missions. By studying Oumuamua and Borisov, we're learning what natural objects look like when they cross between star systems. This helps us understand what our own interstellar probes might encounter, what hazards exist in the space between stars. Scientists have calculated that interstellar space contains about 1 hydrogen atom per cubic centimeter. That sounds like almost nothing, and it is. But when you're traveling at 20% the speed of light, colliding with even individual hydrogen atoms releases significant energy. A spacecraft moving that fast would need shielding against this cosmic rain, and Voyager's measurements help us design that protection. There's also the question of what we might find. Oumuamua and Borisov were the first interstellar objects we detected, but they certainly won't be the last. As our telescopes improve, we'll discover more of these visitors, and each one will tell us something new about planet formation, stellar evolution, and the diversity of objects in our galaxy. The Vera Rubin Observatory, currently under construction in Chile, will begin operation soon and is expected to detect dozens or even hundreds of interstellar objects over the next decade. Each discovery will refine our understanding of what's normal and what's strange in the cosmos. What strikes me at my age is how all of this connects. Voyager was launched to study our solar system's outer planets, a mission it completed brilliantly. Then it became an interstellar explorer, leaving our solar system to study the space between stars. Now, with the discovery of interstellar visitors passing through our neighborhood, Voyager's journey has come full circle. It's showing us what these visitors experienced during their long travels, while carrying its own message outward to whatever or whoever might someday find it. The golden record won't degrade significantly for billions of years, long after Earth has been consumed by the sun's expansion into a red giant, long after our sun has burned out and become a cold white dwarf, long after humanity has either spread across the stars or disappeared entirely. Voyager will still be out there, still carrying its message. The pulsar map on the record uses the precise rotation periods of 14 pulsars to triangulate Earth's location. But pulsars slow down over time, and their periods change. In a few tens of millions of years, the map will be outdated. Any civilization finding Voyager would need to work backward, calculating how pulsars decay, to figure out when the spacecraft was launched and where its creators lived. They would need to be advanced enough to solve that puzzle. Some scientists have suggested that finding Voyager is so unlikely as to be effectively impossible. The galaxy is vast beyond human comprehension, containing 200 to 400 billion stars and perhaps 1 trillion planets. Voyager is a single tiny object, moving at a fraction of the speed of light, through an ocean of space so large that even light takes 100,000 years to cross it. The odds of Voyager passing close enough to any planetary system to be noticed are vanishingly small. But others point out that we found Oumuamua and Borisov, objects much smaller than Voyager, from the tiny vantage point of a single planet orbiting a single star. If we can detect interstellar visitors, then perhaps advanced civilizations around other stars can too. Maybe there are networks of civilizations that routinely monitor their stellar neighborhoods for anything unusual. Maybe they have technologies we can't imagine, capable of detecting even small objects across vast distances. Maybe the golden record will be found, not by chance encounter, but by deliberate search. What I find most moving about Voyager's journey is what it says about hope. In 1977, when Voyager launched, the world was in many ways darker than it is today. The Cold War was at its height. Nuclear annihilation seemed possible at any moment. Environmental destruction was accelerating. Yet the people who built Voyager and created the golden record believed in a future worth reaching for. They believed that humanity would survive, that we would spread beyond Earth, that someday we might join a community of civilizations among the stars. They believed this so strongly that they spent time and effort crafting a message to beings who might not exist, who might never find it, on the chance that our better nature would prevail and we would become something worthy of being remembered. I've lived through the entire space age. I watched the moon landings as a young man, saw the space shuttle era come and go, witnessed the construction of the International Space Station, and now, in my final years, I'm watching private companies land rockets vertically and make plans to settle Mars. I've seen us discover thousands of planets orbiting other stars, places that were pure speculation when I was young, but are now mapped and catalogued. I've watched our understanding of the universe expand from one galaxy to hundreds of billions of galaxies, from 9 planets to thousands, from wondering if we're alone to knowing that the ingredients for life are everywhere. And through it all, Voyager has kept going, farther and farther from home, sending back its whispers from the edge of interstellar space. When I think about what might happen in the centuries and millennia after I'm gone, I imagine Voyager still out there, still carrying its message, still representing the best of what we were and what we hoped to become. I imagine it passing through the darkness between stars, perhaps occasionally crossing paths with other interstellar wanderers like Oumuamua, two messengers from different worlds, briefly sharing the same cosmic neighborhood before continuing their endless journeys. Right now, as I speak to you, Voyager 1 is approximately 15.3 billion miles from Earth. It has traveled farther than any human-made object in history. It is more than 165 times the distance from Earth to the Sun. If you wanted to drive to where Voyager is now at highway speeds, it would take you more than 19,000 years. If you traveled at the speed of a commercial airliner, it would take about 2,000 years. Even light, the fastest thing in the universe, takes more than 22 hours to make the journey. Yet we can still communicate with it. Every day, the Deep Space Network's massive antennas turn toward Voyager's position and listen. Sometimes they send commands, check this system, activate that instrument, tell us what you see, and Voyager responds, its signal so weak that by the time it reaches Earth, it carries only a millionth of a billionth of a watt of power. To put that in perspective, a typical light bulb uses about 60 watts. Voyager's signal, after traveling billions of miles, arrives with 1/quintillionth of that power. Yet sophisticated receivers can detect it, amplify it, and decode the messages it carries. What is Voyager telling us right now? It's measuring the density and temperature of the plasma in interstellar space. It's detecting cosmic rays and determining their energy and composition. It's monitoring the strength and direction of magnetic fields between the stars. It's telling us about the structure and dynamics of the heliopause, the boundary region where our solar system ends. All of this data is unique, irreplaceable, precious. No other spacecraft has ever made these measurements. No other mission has the opportunity to study interstellar space from the inside. And what about the interstellar visitors? What are they telling us? Oumuamua showed us that interstellar objects can be strange, that they can behave in ways that challenge our understanding. Borisov showed us that they can also be familiar, that the processes that create comets and asteroids work similarly across different star systems. Together they've proven that our solar system is not isolated, that we are constantly being visited by travelers from other stars, and that if we watch carefully, we can learn from them. The next generation of telescopes will reveal more. The Vera Rubin Observatory will scan the entire visible sky every few nights, automatically detecting anything that moves or changes. It will find interstellar objects when they're still far away, giving us time to study them properly, perhaps even to send spacecraft to intercept them. NASA and ESA are already planning such missions, designing probes that could launch on short notice when a particularly interesting interstellar visitor is detected, racing to catch up and fly alongside it, studying it up close before it leaves our solar system forever. Within my grandchildren's lifetimes, we may have our first samples of interstellar material, fragments of other star systems brought back to Earth for detailed study. We may have close-up images of these visitors, showing us their shapes, surfaces, and compositions in detail. We may even have sent our own missions to nearby star systems, tiny probes accelerated by powerful lasers, crossing the vast distances between stars in decades rather than millennia. But Voyager will still be out there, older and more distant, carrying its message to the future. In 40,000 years, it will pass within 1.6 light-years of the star Gliese 445. That's close in galactic terms, but still unimaginably far. 1.6 light-years is about 9.4 trillion miles, more than 600 times Voyager's current distance from Earth. In 300,000 years, it will pass near the star TYC 313552-1. In billions of years, it might encounter a solar system, a planet, perhaps even a civilization. What will they make of the golden record? Will they be able to decode it, to understand the greetings in 55 languages, to hear the music of Bach and Chuck Berry, to see the images of people and places from a world that may no longer exist? Will they wonder about the beings who built this vessel and sent it into the void with such careful intention? Will they recognize the mathematical constants and physical laws encoded in its structure, the universal language we hoped they would understand? Or perhaps they'll never find it. Perhaps Voyager will wander the galaxy forever, a ghost ship from a civilization that rose and fell, its message forever unread, its purpose forever unfulfilled. But even that has meaning, even that testifies to something important. It says that we were here, that we looked up at the stars and wondered, that we built a machine capable of leaving our solar system and sent it on an endless journey with a message of peace and hope. I'm old enough to remember when none of this existed, when spaceflight was impossible, when leaving Earth was a dream, when the stars were unreachable points of light with no planets, no visitors, no messages traveling between them. I've watched humanity take its first steps into space, watched us reach the moon, watched us send machines to every planet in our solar system and beyond. I've watched us discover a universe more vast and strange and wonderful than anyone imagined. And I've watched Voyager, that small machine built by a young civilization, taking its first tentative steps toward the stars, travel farther than anything we've ever made, carrying with it the hopes and dreams of billions of people who will never see it again. That, to me, is the greatest achievement of the space age. Not that we could build such a machine, though that's remarkable, not that we could send it so far, though that's incredible, but that we chose to. That we looked at the stars and said, yes, we want to be part of this, we want to reach out, we want to say hello to whatever or whoever might be out there, even if they never answer, even if they never exist. That choice, that gesture toward the unknown, that message of hope sent into an uncertain future, that's what makes us human. That's what makes us worth remembering. And as long as Voyager keeps transmitting, as long as those weak signals keep crossing the billions of miles between us, we'll keep listening. We'll keep learning. We'll keep reaching for the stars, just as we always have, just as we always will, as long as there are humans to look up at the night sky and wonder what's out there. The universe has sent us visitors from beyond our solar system. We've sent our own messenger outward to the stars, and somewhere in the vast darkness between them, in the space where starlight dims and cosmic rays dance, these journeys continue. Both the natural travelers like Oumuamua and Borisov, and the intentional messenger that is Voyager, all moving through the same interstellar medium, all part of the same cosmic story. A story that began billions of years ago when our galaxy formed, that continues today as we watch and listen and learn, and that will go on long after we're gone, as Voyager drifts onward, carrying its golden record into an unimaginable future. That's the wonder of it all. That's what takes my breath away, even now, after all these years, after all I've seen. We are small, we are brief, we are fragile, but we reached for the stars anyway. And in doing so, we became part of something eternal,